Hello everybody, welcome to the intermediate value theorem. This is actually attached to the end of chapter 2.2, but it's such an important, awesome topic that I thought it deserved its own video. What we're going to discuss is how we can use this theorem to approximate zeros of a polynomial, and we're also going to formally define it. So let's get started. Alrighty, an intermediate value theorem. Here it is. Let's get you the formal math speak definition. So, for any polynomial, which is a continuous function like we talked about before, for any continuous and therefore, or for any polynomial and therefore continuous function, what we can say is that there's going to be some a value, some c value, and some b value. And that also means that there's going to be an f of a value. Ooh, I should have made that up higher. That's okay. An f of c value, and there's also going to be an f of a b value. Okay. Maybe let's make those different colors. So let's call this one the a one. This goes to f of a. You go to f of b. There we go. That's a little bit easier to see. And then we can call you the blue one, or we'll just leave that c value plain. Okay, great. So this is the graph we're going to look at when we make our definition. And here's what the intermediate value says. It says, let a and b be real numbers such that a is less than b. Okay, so far they are. A is over here, B is all the way over there, so A is definitely smaller than B. If f, fancy f, so if the function is a polynomial function such that f of a is not equal to f of b, and it certainly is not. This value is not this value. Those values do not equal each other. Then we can say that f takes on every value between f of a and f of b. It's kind of like a no-dir sort of theorem. Basically, it's saying that for a continuous function, a function that doesn't do any of those jumps or doesn't do any sort of holes or anything like that, it just flows really nicely the whole time. I would never pick up my pen if I drew it. For any function that's continuous, especially polynomials, we know polynomials are continuous, then basically between one value of x and a bigger value on x, between an a and a b, you will have a y value for every single one of those x values. And that's true for this graph very clearly. There's no holes, no jumps, no nothing. So for every single x value in here, there's going to be a y value. Great. Basically, this just defines a prettier picture of what it even means to be continuous, right? Okay, so here's how that's useful. We're going to write a little note to ourselves. Why this is, useful. Here's why. If f of a and f of b are opposite signs, there must be a 0, a root to our polynomial between them. Between A and B. And that's just such a revelation, we're going to put an exclamation point next to it. Wow, how cool. And here's a little picture as to why. So say if we had our y-axis and we have our x-axis. We know that we have all of our positive y values up here and we have all of our negative y values down here. So if at any point, let's say, I don't know, at 1 our graph is positive. Let's say at 1 our graph is 2. Cool. And then we find that, I'm not sure, maybe over here at 3, our graph is now -1. Because there has to be an f value for everything between here and here, because there has to be a y value for everything between here and here, our graph would be a line between this point and this point. It might do some funky stuff. It might like go up and down, I don't know, but we know for sure it has to go from here to here without stopping. That means that it must cross the x-axis at some point, let's say right here, I'm not sure, and it would have a 0 between this A and this B value. Let's just put little arrows at the end of this. Between this A and this B, there would have to be a 0. And same thing if, say, A started out on the negative side, right? Here's negative for y, here's positive for y. I'm not sure. Maybe we had a point at -1, let's say -2. -1, -2. And then we found over here, when x equals 3, that we had a positive value of 1. Again, because there has to be a y value for everything between this A point we chose and this B point we chose, because my line is never going to stop. I never break, I never jump, I never do anything. There has to be a 0, a point where my A crosses, or pardon me, where my graph crosses the x-axis to get from A to B. It could look like that, for example. I'm not sure. The point is that there would be a point where from this negative value to this positive value on the y, we would have to cross the x-axis at some point to get there. Let's do an example of this. So, for the function, we have a little fancy f equals x cubed plus x squared plus 1. We're asked the question, does a 0 exist on the interval -2, -1? And we could look at a table right now, just for the sake of time and the fact that I know that these numbers work. We're going to substitute in -2 and -1, and we're going to see what happens to the signs of these values. Remember, this is kind of like our A right now, and this is kind of like our B. We want to see if we're going to get opposite signs for our A and for our B. So let's substitute those in. If we take f of -2, if we evaluate our function at -2, we get -2 cubed plus -2 squared. This is kind of a bad 2, sorry. Plus 1. We get -8 plus 4 plus 1. We get -3. If we evaluate our function at -1, we get -1 cubed plus -1 squared plus 1. So we get -1 plus 1 plus 1, we get 1. Oh my goodness, look at that. We have a negative value for our A and we have a positive value for our B. That means that at some point, somewhere between -2 and -1 on our x-axis, there is a point where our graph crosses the x-axis. How interesting. Okay. And when we graph x cubed plus x squared plus 1, Holy smokes, we totally prove our point. Let's do that. Let's graph this. Let's call this -1. Let's call this -2. And we'll call this guy out here 1. And we'll call this guy right here 1. We'll go down 1 to -3. All right, here's a few things we already know. We already know there's a point -2, -3. We already know there's a point -1, 1. Whoa, how cool. And actually, what we can do to kind of help ourselves with the rest of the graph is we can take a look at our calculator, and we can put that in there. So we can do y equals x cubed plus x squared plus 1. When we graph it, oh, I have to fix my window range, so I'm going to quit out of that. I'm going to go to zoom, and I'm going to go to zoom. I'm going to go to zoom fit. That should fix things. I want to get closer to -1, -2, so I'm going to press zoom in. And I started over there. I want to look right here. Right here. So I'm going to zoom in more. How cool. All right, it looks like, or you know what? Let's change my window just to fit what I'm trying to do. Pardon me for being so picky here. But let's take a look. Let's make this go from -3 to +2. And let's go from -4 to +2. Let's try that. That'll be a little bit prettier. There we go. That's what we want to see. All right, so we can see that from -2 to -1, there is in fact a 0. It looks like it's gone right between. So when we continue to make our graph here, we go up a little bit more, not really, and then we go through 1 and we go back up. Awesome. And what we can say about this is, let's label our graph first. This is f of x equals x cubed plus x squared plus 1. What we can say here is that f, fancy f, has a 0 in the interval -2 to -1. All right. Let's do another example of this. Let's use, I'm going to abbreviate here, IVT, did I say that correctly? Yeah, intermediate value theorem, pardon me, to approximate the 0 of f of x equals x cubed minus x squared plus 1. Okay, pretty similar, but a little bit different. And what we're going to do here is we're going to take a look at our table to approximate this one to see what intervals this might be happening on. So we're going to take our function, we're going to put it into our grapher. We're going to say x cubed minus x squared plus 1, kind of similar to the last equation. And we're not going to press graph, we're going to press second window to get our table going. We want to take a look. Let's see at about -2. And we're going to change by 1s, and then we're going to go second graph to take a look at our table. Okay, so it looks like negative, and then positive. Oh, look what just happened there. It looks like we were negative, and then we go positive, positive. But right here is where something interesting happens. From the x value -1 to 0, we were negative in our y, and then we got positive in our y. We went from -1 to +1. So we know, using the intermediate value theorem, that there has to be a 0 in between -1 and 0. So what we can do now is we can break up that interval even more. We can take a closer look between -1 and 0, and here's how we can do that. We can press second window. We can take a look from -1 this time. We want to look from -1 to 0, And we want to change not by ones anymore. We already did that. We want to change by something smaller. Let's change by 1/10. So let's change by 0.1. And let's see what's happening at 0.9, 0.8, 0.7, and so on. We're going to press second graph. Okay, now we're taking a closer look. It looks like it still goes negative at -1. At 0.9 it's negative. At 0.8 it's negative. Okay, here we go. So it looks like there's definitely a 0, specifically not just between -1 and 0, but between -0.8 and -0.7, because we go from negative to a positive. And guys, we can keep on doing this. We could start our table at -0.8. We could change by 0.001, and we could take a look to see what is really happening there and at exactly what point we get a 0. You can keep on doing that to get more accurate. However, we're going to call it good here, and we're going to say that there is a 0 that exists in the interval -0.8 to -0.7. And here's what else we're going to do. Our calculator can get even more accurate. We could keep on approximating, but to find exactly where that 0 is, what we could do is we could press graph. And our previous window still works for this. What we can do is we can see that's where the 0 is, right between that -0.8 and that -0.7. And what we're going to do now is we're going to press second calc. We're going to go down to 0. And we're going to pick a point to the left of our 0. And we're going to pick a point to the right of our 0. And now it's going to guess for us. And there we have it. It found the 0 at exactly 0.755. We'll round to 3 places. And we'll have our final answer of the 0 of the function occurs at x equals negative 0.755. Pretty cool stuff. Next, let's talk about an example with finding intervals. And then I'll totally leave you alone. But say we're given the function f of x equals x to the 4th plus 2x cubed minus 3x squared minus 4x plus 2. And we're asked the question, in what intervals are there zeros? We're going to use our table to help us with this one. So what we're going to do is we're going to put it in our grapher again. And we're going to do our function x to the 4th plus 2x cubed minus 3x squared minus 4x plus 2. And again, we're not going to go to graph right away. We're going to go to table set. And we're going to take a look at when our values begin at -4. And we're not interested in small changes like we were last time. We're not interested in tenths. So let's just go by ones. Look at every one. And now we're going to press second table. Okay. And when we take a look at these values, what we can see is that there appears to be a 0 between -3 and -2. And I know that because our y values start positive at -3 and then they get negative at -2. So we can say, so far, there are zeros in the intervals -3 to -2. And it's also important to understand how many zeros we're going to be looking for, right? The degree of our polynomial is 4. N value is 4. That means there can be at most, I'm just going to write a little note to ourselves in here, at most 4 zeros, at most 4 intervals. So we know once we get to 4, we can stop. All right, so to go from -3 to -2, there's definitely a 0 in there. Positive, positive, okay. And if we take a look from 0 to 1, we go from +2 to -2, so there's definitely a 0 in there. You can say from the interval 0 to 1. If we continue down our table, we can see it went from positive, and then it was +98, positive, and then negative. I didn't catch that. Okay, my bad. It went from -2 to +14. So there's definitely a 0 also between 1 and 2. And I'm realizing I missed one previously. I missed one. If we take a look again back between, there we go. We talked about going from -3 to -2. We went from +14 to -2. That was definitely a 0. But then take a look here. To go from -2 to -1, we had a negative and then a positive y. Negative to positive means there's also a 0 there between -2 and -1. And again, I know I'm good to go. I can stop now because there's 4 intervals here. That means there are 4 zeros, and our degree was 4, so that's the most this polynomial is going to have. That's all I have for you. We'll see you in class tomorrow.